In section 10.1, we're going to get an introduction to systems of differential equations. Primarily, we're going to be looking at the why. Why do I even have systems of differential equations? So there are many physical problems that involve a number of separate elements that are linked together in some fashion. So electrical networks is an example, as are fluid mechanics and other types of mechanics, and in plenty of other fields, meteorology, those sorts of things. So in these and similar cases, the corresponding mathematical problem consists of a system of two or more differential equations that we need to come up with a manner to solve. So we're going to explore those different types of systems today. And in the next class, we will spend some time learning how to set them up and how to begin solving them. So for our first example, we're going to talk about two tanks. So we have tanks T1 and T2. T1 contains 100 gallons and T2 contains 300 gallons of salt solutions. Salt solutions are simultaneously added to both tanks from external sources. They're pumped from each tank to the other and drained from both tanks. A solution with 1 pound of salt per gallon is pumped into T1 from the external source at 5 gallons per minute, and a solution with 2 pounds of salt per gallon is pumped into T2 from an external source at 4 gallons per minute. The solution from T1 is pumped into T2 at 2 gallons per minute, and the solution from T2 is pumped into T1 at 3 gallons per minute. T1 is drained at 6 gallons per minute, and T2 is drained at 3 gallons per minute. If we let Q1 of T and Q2 of T be the number of pounds of salt in T1 and T2, respectively, at time t greater than 0, we can then derive a system of differential equations for Q1 and Q2, assuming that both mixtures are well stirred. So if we let the rate in and rate out denote the two different rates at which salt enters and leaves a tank, we can define Q1 prime, the rate at which salt is changing in Q1, in tank 1, T1. We have rate in 1 minus rate out 1. So this is very much what we did in chapter 4. We have the same thing in tank 2. So this is for tank 1, and this is for tank 2. So in Q2, we also have a rate in, but we'll give it a subscript of 2 to match T2, tank T2, and a rate out subscript 2. And we're also going to note that the volumes of the solutions in both T1 and T2 remain constant at 100 gallons and 300 gallons respectively. Here is a diagram of what's going on. You know me and my pictures. I'm always going to have pictures, but this is actually from the textbook. So in T1, we have 5 gallons per minute coming in with a concentration of 1 pound per gallon. And we have 100 gallons in the tank, the volume of the tank here, or the volume in the tank, sorry. And it's leaving at 6 gallons per minute. In tank T2, we have 4 gallons per minute is our rate, at which we have coming in 2 pounds per gallon. It begins with 300 gallons of solution in the tank, and as we stated it on the last slide, it remains at 300 gallons. T1 gets pumped into T2 at 2 gallons per minute, and T2 gets pumped into T1 at 3 gallons per minute, and T2 is being emptied at 3 gallons per minute. We know that T1 receives salt from an external source at a given rate. That rate is 1 pound per gallon times the 5 gallons per minute, or 5 pounds per minute. Found the same way that we did in chapter 4 here. We also know then it's also receiving a salt solution from T2. Now this is where the rate gets interesting, because we have to have a pound per gallon mixture in T2, the concentration, times 3 gallons per minute. And much like we did in chapter 4, we know that that pounds per gallon is going to be Q2 over 300. Q2 is the amount of salt in tank 2 at any given time. So we have Q2 over the 300 gallons it started with, times 3, the rate at which we have new coming in, So we end up with 1 over 100 times Q2, or Q2 over 100, which I believe is the way I wrote it often in chapter 4. So that means that our composite rate for T1 that's coming in would be the 5 from the external source plus the Q2 over 100 from tank 2. So we've got external plus T2, plus from T2. And we know a solution is leaving tank 1 at the rate of 8 gallons per minute. How do we know this? We know we have 6 gallons per minute leaving that are being drained, and 2 gallons per minute are going into T2. So in total, we have 8 gallons per minute that are leaving. So our concentration of salt that's in the tank at T1, we don't really know. So we're going to say that it is Q1 over the amount of solution in the tank is 100 gallons. So Q1 over 100 times the rate at which it's leaving, which is our 8 gallons per minute. So 8 over 100 gives us 2 over 25. So our rate at which tank 1 is being emptied is 2 over 25 times Q1. So if we put it together, our full rate for Q1 is the rate in 1 minus the rate out 1. And in this case, that's 5 plus Q2 over 100 minus 2Q1 over 25. So we've been able to model then what is happening in a physical way in tank T1. In the same way, we can model what's happening in tank T2. Well, we know it's receiving salt from the external source, and we're going to find that rate the same way that we did in chapter 4. 2 pounds per gallon times 4 gallons per minute gives us 8 pounds per minute. We know it's also receiving from T1 at 2 gallons per minute, whatever the concentration is in tank T1, which, well, we don't really know at any time what it is, so we're going to call it Q1 over the amount of solution, which is 100. So we have Q1 over 100 times 2 gives us 1 over 50 Q1, or Q1 over 50. And then that leaves our rate in now is going to be 8, right, from here, our 8 plus our Q1 over 50. That's our total rate in. And now, much like in tank T1, tank T2 has solution leaving at a total rate of 6 gallons per minute because we have 3 gallons per minute that are being drained and 3 gallons per minute that are also being drained into T1. So not just drained specifically from the tank, but also in moving into T1. So our new rate out for tank T2 would be the amount of solution in T2 at any time, which we don't know, we'll call it Q2, over the amount of solution in the tank, which is 300 gallons. So if Q2 over 300 times the total rate, which is 6 gallons per minute. 6 over 300 gets us 1 over 50, so we have Q2 over 50. And one more time for Q2, we have the rate in sub 2 minus the rate out sub 2. If we summarize this in a table, we have Q1 prime equals 5 minus 2 over 25 times Q1 plus 1 over 100 Q2. And Q2 prime equals 8 plus 1 over 50 Q1 minus 1 over 50 Q2. Notice that we now have a system of 2 differential equations. They're both first order, and both of them rely on both Q1 and Q2. So this is a prime example of how a system of differential equations may come about in a very physical way. Just when you thought you were done with spring problems, I'm going to introduce one that involves not just one, but now 2 springs in the same system. So if we look at our system here, we have a mass M1 that is being suspended from a rigid support on a spring S1. And a second mass, M2, is then suspended from the first on a spring S2. And I believe our diagram from the book is actually backwards. This should be S2, that should be S1 and this should be S2. There we go. So the springs obey Hooke's law with spring constants K1 and K2. The internal friction causes the springs to exert damping forces proportional to the rates of change of their lengths, with damping constants C1 and C2. Let Y1 equal Y1 of t and Y2 be Y2 of t. They're both functions of time. And there's a displacement of the two respective masses from their equilibrium positions at time t, where we're measuring positive directions being upward again. So we're going to derive a system of differential equations for Y1 and Y2, assuming that the masses of the springs are negligible and that vertical forces F1 and F2 also act on the objects. So this is where we have to consider the same kinds of system. Well, this system will have the same kinds of forces acting on each mass that we had in chapter 6. It's just that mass M1 is also going to have a force from the second spring and a second mass. So in equilibrium, spring 1 supports both mass 1 and mass 2, and spring 2 only supports mass 2. So this is where I was saying that when we look at it, then we're going to have extra forces acting on M1 than on M2. So therefore, if delta L1 and delta L2 are the elongations of the springs to equilibrium, remember we always use delta L to get us to that from the natural spring length to the equilibrium length, then M1 plus M2 quantity times G is going to equal K1 delta L1, and M2G is going to equal K2 delta L2. And remember, this is because spring 1 here is supporting both mass 1 and mass 2, but spring 2 is only supporting mass 2. If we let H1 be the Hooke's law force acting on M1, and we let D1 be the damping force on M1, we can similarly then say that H2 is the Hooke's law force and D2 is the damping force acting on M2. According to Newton's second law of motion, the sum of the forces equals the mass times the acceleration. So in this case, the sum of M1 Y1 double prime, which is the acceleration of mass 1, is going to be the force due to gravity plus the force due to Hooke's law plus the damping force plus any external force. So this is gravity, our spring force, our damping force, and any external force. And in the same way, the sum of the mass times the acceleration, and sum of the forces equals the mass times the acceleration for spring 2, or sorry, M2 as well. We end up with it having the force on it due to gravity plus a spring force plus a damping force and plus an external force. And we know in practice sometimes these other forces aren't there. Sometimes we aren't damping. Sometimes we have no external forces being added. Right? So we know that it's possible that some of these terms could go to 0. So when the displacements are Y1 and Y2, the change in the length of S1 will be negative Y1 plus delta L1, and the change in the length of S2 is negative Y2 plus Y1 plus delta L2. Remember, this is because, don't forget, not only is now spring 2 moving the length that the force is pulling on spring 2, it also you have to add to this displacement here the amount of displacement we had on L1. So that is our, on M1. This is our delta L2 minus Y2 and plus Y1. So both springs exert Hooke's law forces on M1. This is what I mentioned earlier. And S2 only exerts a Hooke's law force on M2. So these forces are in directions that tend to restore the springs to their natural lengths. So therefore, H1 would equal K1 times negative Y1 plus delta L1, right, which we had here, right, the change in length of S1, minus K2, now this is for spring 2, negative Y2 plus Y1 plus delta L2, right, the displacement, the change in the length of S2. And then we have H2 being just K2 times this displacement, negative Y2 plus Y1 plus delta L2. When the velocities are Y1 prime and Y2 prime, spring 1 and spring 2 are changing length at the rates of negative Y1 prime, and that's only for mass 1. For mass 2, we've got negative Y2 prime plus Y1 prime, because the velocity of the first spring is also going to affect what's happening. The velocity of the mass attached to the first spring is going to have an effect on the mass attached to the second spring. Both springs exert damping forces on M1, while S2 only exerts its damping force on M2. So since the force due to damping exerted by a spring is proportional to the rate of change of the length of the spring and in a direction that opposes the change, it follows then that D1 equals negative C1 Y1 prime plus C2 times Y2 prime minus Y1 prime. And D2 then would be negative C2 times Y2 prime minus Y1 prime. Taking all of these values that we've just defined and plugging them in to our two equations where we were summing all the forces allows us to boil down the system to M1 Y1 prime, double prime, equaling negative C1 plus C2 quantity times Y1 prime plus C2 Y2 prime minus the two spring constants added together times Y1 plus K2 Y2 plus the external force on spring 1. M2 Y2 double prime then can simply be written as C2 Y1 prime minus C2 Y2 prime plus K2 Y1 minus K2 Y2 plus the force acting on spring 2, external force. This is a system of differential equations. I didn't put it in a box this time, but we have here a Y1 double prime on the left, a Y2 double prime on the left, and on the right-hand side we have all of our equations are in terms of Y1, Y2, and their first derivatives. So our first example was a first order system of ordinary differential equations. This one is an example of a second order system of differential equations. There are no homework problems for this section, but I wanted to introduce you to the concept of how do systems of differential equations come about.